So, of course, Mendel did his predictions of heredity using pea plants. We can do the same with pea plants. We can do the same with human traits. And what Mendel did, and the way that it's easiest to set these things up, is first to track a single trait. They call it a monohybrid cross. And let's say we're looking at flowers. The easiest way to do this is to start with what we call a true breeding set of parents. And by that we mean that one of the parents is homozygous dominant for the purple allele. Both copies of the gene are the purple allele. And one parent that is homozygous recessive. Both copies of the allele are the recessive allele. And so you cross that generation. They call it the parental generation. And again, one of the easiest ways we do that is through something called a Punnett square. So I want to show you what a Punnett square would look like for this situation. So let's say we're interested in flower color. We're going to start with our true breeding, right? So this is our purple flower, homozygous dominant. So this is our parental generation, or sometimes they call it just the P generation. And we're going to cross this purple plant, or purple flower, right, with a plant that has white flowers. So this is the homozygous dominant, cross to the homozygous recessive. Okay. And we can visualize this using what's called a Punnett square. So you might remember this from other biology classes you've taken, but since we're looking at, right, 1, 2, 3, 4 genes, or 4, copies of the gene, 2 from each parent. We do big P, so we have one parent on top, little p, one parent on the side, and we draw a square that has the number of alleles that we're dealing with. So if I have a big P, over here I have a little p, I bring down the big P, I bring over the little p, I bring down the big P, bring over the little p, same thing, bring down the big P, bring over the little p. And now this is what they call filial 1 or F1 generation. And I can count them up. So I have, in this square right here, I have big P, little p, and I like to use tally marks. So I have 1 tally. This is big P, little p, there's 2. Big P, little p, 3. Big P, little p, 4. So the way that I would say this is that 100% of my offspring, this is the genotype. They are heterozygous. Okay, they're all this genotype. Well, big P, little p equals purple, right? Anytime, because purple is dominant. So every big P, no matter what, that's going to be purple. So purple is my phenotype. So 100% purple. Okay, so this is what Mendel saw, right, when he looked at his P's. But now where it gets interesting is what happens in the next generation, the filial F2, or the F2 generation. So in the F2 generation, you take these heterozygotes and you cross them. Now the way you set up the Punnett square is, right, now you're going to cross a big P little p with another big P little p. So you make your Punnett square big P, little p, big P, little p. Okay. So you bring down the big P, bring over the big P, bring down the little p, bring over the big P. Bring down the big P, bring over the little p, bring down the little p, bring down the little p. Okay, so now this gets interesting. I'm going to start up here again because I like to start in the upper left. I have big P, 1. Okay, next. So I've done that one. So now I have a big P, little p. Here I also have big P, little p. Here I have little p, little p. So now I have, okay, this is going to be purple. So I have one purple. This one's also going to be purple, but there's two of them. So purple. But this one will be white. And so if I add up, right, I have purple plus 2 purple, I get 3 purple, 1 white. And so what we tend to see when we start with true breeding parents, we cross the heterozygotes, we see a 3:1 phenotype ratio when we look at the F2 generation. So what I want you to notice here, right, purple and white in the parents, or I guess the grandparents, right? These would be like the grandparents. The parents are all purple, and then the grandchildren, or the children, right, are purple and white. So we get that recessive trait to show up again. So we do see this in humans. The recessive trait, we kind of say it colloquially, the recessive trait skips a generation. And that's why the recessive trait skips a generation. So again, we can measure using one of those Punnett squares like we just did. This is what Mendel saw with his pea plants. This is also what we see in humans. What we could think about is, what if this is a genetic condition that follows this same pattern, where you have a dominant gene and a recessive gene? Maybe cystic fibrosis, for example. If two people are carriers for cystic fibrosis, what that means is that they are the heterozygotes. They have the normal allele and they have the mutated allele. But because they have the normal allele, they look normal. They don't look like they have cystic fibrosis. The normal allele can hide the fact that they're carrying the mutant gene. So if you have two people who both carry that recessive trait for cystic fibrosis, they have children, there's a 3/4 chance for each offspring, right? There's a 3/4 chance that the offspring will be normal in terms of not having cystic fibrosis, because the offspring could be homozygous dominant or heterozygous. But there's a 25% chance that they will have a child with cystic fibrosis. So that can be why it's very important for family planning. You might think about, does one of these conditions run in your family? Is there an aunt or a grandparent or somebody who had a condition like this where you could be a carrier? The same thing for your partner. Is there a condition that runs in their family? And you can do genetic testing to determine your risk. So, what do we see here? How did Mendel interpret this? Well, he called it the law of segregation, that each parent contributes one allele for a gene during gamete formation. So if you have the heterozygote, right, carries one dominant allele, one recessive allele. When they are going to make their gametes, the gametes segregate, right? The chromosomes segregate, and one gamete gets the dominant allele, one gamete gets the recessive allele. And that's how we can get that 3-to-1 ratio we saw in the F2, and how recessive traits, like we see here, can skip a generation and pop back up again.